Drama begins and it never ends.
Oh my gosh.
Good afternoon, everybody. Today we're going to talk about induction some more. I'm going to go back to a few set theory things that you'll need for homework 5. And if we have time, we'll start on recursion. So by the end of today, you'll be ready to do everything that is on homework 5. So let's review why we do induction in the first place. So can someone remind me what induction is for? We've been doing a lot of proofs, right? And induction is a type of proof. Why do we do induction?
For large sets or
for infinite sets,
sets.
such as all of the integers, right? So the whole point is we want to prove something for an infinite set. So induction, again, was where we had a basis, something like P of 1. A predicate was true for the value of 1. And then we had to prove for all k, where k is greater than or equal to 1, that P of k logically implies P of k plus 1. So this is the first principle of induction. This is one kind of induction. There's a few kinds, but they're all basically the same, that you prove a starting point and you prove going from one step to the next. And we'll talk about that some more when we talk about recursion, because recursion defines sets sort of inductively or recursively. You start out with a basis and you tell a rule for making new things, and so induction will be a way that we prove things that are true for recursively defined sets. So if I define a set recursively, I can do induction with that also and prove that things are true in that set. Yes?
Is that the same thing as modus ponens?
Yes, we do use modus ponens. That's what these two things together, along with modus ponens, give us that P of n is true no matter what n is. So P of n is true for all n greater or equal to 1, after these two things are true. That's what modus ponens gives us, right?
Okay.
That's excellent that you noticed that. That's why induction works, is because of modus ponens. And this is another reason why we had predicate calculus, is so we could talk about the definition of induction, which has predicate calculus in it. So let's do, last time we proved the summation from k equals 1 to n. And if you notice, most of the time I'm going to use k as my index for summation, because i's are a little hard to read and hard to tell the difference from 1's, right? So last time we talked about the summation k equals 1 to n of k is equal to n times n plus 1 over 2. And this is a really handy summation to know anytime that you're going to be doing analysis of algorithms, or it's actually handy a lot whenever you have any kind of summation show up. And just to make sure you understand what this means, if I do summation k equals 1 up to n squared of k, what's my formula on the right-hand side going to be?
N squared times n plus 1 squared over 2.
N squared.
Sorry, n squared.
N squared plus 1.
It's n squared plus 1 all over 2. Right, so wherever the n is, I plug in n squared. So whatever happens to be on the top is what goes in that formula. So I'm sorry for scratching that out. That was n squared times n squared plus 1 over 2. So whatever is on the top is what goes in that formula. And it matters what's on the bottom, right? So if I started with 1 on the bottom, it's going to give me this. What if I start with 2 on the bottom? What's the difference?
It's the same thing minus the 1.
Right. It's the summation k equals 1 to n of k minus the very first term, which happened to be 1. Right? So that would have been, I can substitute in n times n plus 1 all over 2 minus 1. So if you want to use that formula, but you have different ranges, now you know how to change it.
How did that happen again?
Well, if I start from 2, if I go from 2 to n, and I add those numbers up, okay, so this means I add 2 plus 3 plus 4 plus 5 plus 6 plus 7 all the way up to n. That's the same thing as adding 1 up to n, except I have to take the 1 back off. Okay.
So if that was 3, you would subtract.
Right. If I had summation k equals 3 up to n of k, that would be summation k equals 1 up to n of k minus summation k equals 1 up to 2 of k. Right? And this would just be, this would be just 1 plus 2 right there. That's what that summation is. Yes?
If k was squared, would it be n plus 1
If
plus...
k is squared, you'll have a whole different story.
Okay.
Right? It'll be a lot bigger. We could try to come up with a closed form for the summation of k squared. Let me check my notes and see if I
Isn't it
actually
n
have-
plus 1 times 2n plus 1 divided by 6?
I couldn't tell you that. I would have to figure it out.
That makes sense. It's like, this is a step. You subtract like this.
So we could try to figure out a closed form for that. Let's guess. If we don't get it very soon, I won't waste the class time doing it, but we'll see if we can figure it out. So if we have n here, and summation k equals 1 up to n of k squared, we'll figure out what that is. Okay, so where n equals 1, that's just 1. Where n is 2, that's 1 plus 4 is 5. For 3, that's 1 plus 4 plus 9, which is 16. So this is just 16
Sure,
plus
that's
4,
not
right?
14?
Can I not add? Sorry, plus 9 is 14. You're right. And then if I add 4, it's 18. Now you all see why I can't do anything in my head, because I can't do it on paper either, right? So I'll write everything down. 23 plus 6.
Bracket step number 4. Shouldn't the 4 be squared? So it would be 14 plus 16.
All right, we're not doing this problem. You can look it up in
I
a
was
book.
basically just asking, I mean, I wanted to know how you
You
would
can't
figure that
modify
out.
the formula if you change the function on the inside. If you change
Okay.
the function on the inside, then the formula
Doesn't work.
apply.
Okay, that's what I wanted to know.
If you can figure out how it changes each of the terms, you could do it.
Okay.
But that changes each of the terms depending on which term it is. So it's different for every term, so you can't just change the formula on the right-hand side without doing a table and checking it.
Would you put that last one back up real quick?
No, I was missing
No,
that
not
one.
the one before it.
Sure, I should put
Yeah,
that
that
one.
one.
Formula.
I think that's it.
Yeah, if I got a question.
necessarily.
From
This is
k
adding
to
the summation.
k equals 1 to 2. How did you say it's 1 plus 2? That's 3. I thought there would be only 2.
It just goes up to 2. I don't want to subtract the third one off because if I subtract the third one off, then I won't have it for this one. This one on the left should be 3 plus 2 plus 4 plus 5 plus 6 all the way up to n. This one starts 1 plus 2 plus 3 plus 4. So if I want the 3 still on there, I need to subtract 1 to 2. So that gets me to what I wanted to do was draw a picture for summations for you. So anytime you have a summation and you need to do a proof, you're going to know how to split it up. So, and in order to do that, I'm going to show you a problem. So remember that we said that if I have k equals 1 and I change this top number, let's just say I have 3n here. That's going to change my formula. So I have 3n times 3n plus 1 all over 2. I'm going to teach you my little secret for making up new problems. The summation for k equals 1 up to 2n minus 1 would be what?
Plus 1 at the end.
2n minus
2n
1
minus
times 2n.
2n minus 1 plus. Yeah.
Okay.
Right.
Now, if I subtract the left-hand sides here and the left-hand sides here, I'll come up with a new formula, right? So I'm going to get, if I subtract these two, what summation do I get? K starts at the next thing after 2n minus 1, which is what? 2n.
2n.
And it goes all the way up to 3n, right? So if you think about it, we had from 1 up to 2n minus 1 in the first summation, right? All of those numbers. And the second one went all the way up to 3n. So if I subtract those two, I have the stuff after 2n minus 1, which starts at 2n. So the first summation, which is summation k equals 1 to 3n of k, is equal to the sum of these two summations, right? This is the summation k equals 1 up to 2n minus 1 of k. And this is the summation k equals 2n up to 3n of k.
But isn't there a slight gap there between 2n minus 1 and 2n?
There's a gap, but we're only talking about integers because our summations only go k equals 1, 2, 3, 4, 5, 6, 7, 8. So the gap is not really there because these are two consecutive integers.
Okay.
Right? 2n minus 1, the next highest number is 2n.
Gotcha.
Highest integer is 2n.
Right.
That's the meaning of this.
So that's the next integer. So the left-hand side is the summation from 2n to 3n of k. Yes?
I'm not sure how you got 2n times 2n divided by 2 for...
This was using our summation. If we had k equals 1 up to n of
Minus
k,
1 plus 1.
that was equal to n times n plus 1 over 2. Right?
Yeah, okay, that's
So
good.
if I
Okay.
do that, if I put 2n minus 1 into this formula, I get 2n minus 1 for the first term, and I get 2n for the second term, because I have n plus 1 here,
Oh, okay.
right?
Oh, so
I
you're
take
just
2n
plugging
minus
it into
1
that.
plus 1.
Okay.
I get 2n and divide
But
by
what's
2.
the little minus sign out in front? Are you saying that that's...
The minus sign is I'm going to take the left-hand sides and subtract them, and the right-hand sides and subtract them. I'm going to take this equation and subtract it. I'm going to take this second equation and subtract it from the first one.
okay, that's what I didn't see. Okay.
Okay. That is not necessary to understand the equation.
Right, okay. But those two equations are what you're getting for the third one?
I'm using those to derive the third one.
Right,
I'm
okay.
showing you how to derive a homework problem. Okay? Because we need to solve this problem. I want to solve this problem, and I didn't derive it beforehand, so I have to do it now. So that's going to be 3n times 3n plus 1 all over 2 minus 2n minus 1 times 2n all over 2. Right? So that's actually how you would come up with a formula if you had a summation from some strange value up to another strange value. You would start it at 1, use the formula that you know, and subtract another summation using another formula that you know. So if I saw this summation 2n to 3n, I could come up with the formula on the right using these two that I know up at the top. Yes?
Isn't it quantity? Subtract the quantity, 2n minus 1, 2n.
Yes, that you can put parentheses around that. But since there's a product there, you assume that the minus distributes on everything. Okay? So I'm going to write that on the next sheet.
Since it's a fraction, some denominator.
Minus 2n minus 1 times 2n all over 2. So let's make this formula a little nicer. That's 9n squared plus 3n minus, that's going to be 2n squared, right? And then plus 2n, and all of that's over 2.
Is that a minus or a plus?
That's a plus, because this minus times that minus gives me a plus.
Okay.
Okay, so this is going to give me 9n squared plus 3n minus 4n squared plus 2n all over 2, which is equal to 5n squared plus 5n over 2. All right, so now we have a summation. We have summation k equals 2n up to 3n of k. And if the algebra is a little hairy for you, you can just check over it when you get home. We're going to prove this by induction. So we derived it from another thing that we proved by induction, but just to check our math, we'll prove this by induction. And it's also to give us some practice using summations. Now, if I say prove by induction, you have to know which case is the basis, right? So what do you think you would choose for a basis here? You can choose whatever you like. But I would choose 1, because normally you want to prove it for positive integers. So I would choose 1. Sometimes I would choose 0, but probably not for this one. So let's start with n equals 1. So again, at the top, we write our problem, so we don't forget what we're doing. Does anybody else think it's cool it came out to look so pretty? I think it's cool. Okay, basis. If you think it's cool, it sure does.
Give us brownie points.
That's just because you work harder when you think things are cool, and that means you get better scores. It doesn't get brownie points if that's what you're asking. So this one's k equals 2 up to 3 of k if I plug in 1 for n, and that equals 5 plus 5 over 2. I'm checking this to see if it's true. So that's equal to 5 on the right, and this left-hand side is 2 plus 3, and that's equal to 5. So I'm done with the basis. Now, as my assumed step, I write down what I'm trying to prove, because I assume it's true up to n. And it's important that you write this step so that you know what you are given, and then you have to write the next step, which is to prove, so you know what you're trying to go towards. So what does k start with here? If I want to prove, remember this is p of n plus 1, this was p of n. So if this is the statement for n, everywhere I see an n in that statement, I have to put n plus 1. So what does that give me on the bottom?
2n plus 1.
So it's 2 times the quantity n plus 1, right? Which gives me 2n plus 2, right?
Yeah.
Goes up to what? 3n plus 3.
Will you repeat that last step? I didn't catch that.
In that step, everywhere I had an n in the assumed statement, I'm going to put n plus 1. In this statement here, I multiplied 2 times n. So if I'm putting in n plus 1, I have to multiply 2 times n plus 1, which gives me 2n plus 2. Same thing for the top.
And that's part of the rule that you do from n to n plus 1?
Absolutely.
Right, okay.
Absolutely. This is a function of n, so every time I change, if I go to n plus 1, I have to, everywhere there's an n, I replace the n with n plus 1. I don't just add a 1 everywhere I see an n. So on the right-hand side, that's 5 times the quantity n plus 1 squared, and then 5 times the quantity n plus 1 all over 2. So these, how many points do I get so far?
16%.
60%. There you go. So I've got 60%, and I haven't had to do very much yet. But this is very important, is putting in n plus 1 correctly, right? But if you do it just like a machine, automatically put n plus 1 everywhere there was an n, and don't try to do too much in your head, you'll get the points. All right, so from there, let's just go ahead and make this proof statement a little simpler to look at. So that's going to be 5n squared plus 10n plus 5 plus 5n plus 5 all over 2. And that's equal to 5n squared plus 15n plus 10 all over 2. So that's the statement we're going to try to prove, that summation k equals 2n plus 2 up to 3n plus 3 of k is equal to this formula on the right. Now what we do is we start with the left-hand side of what we're trying to prove. We try to write it in terms of the left-hand side of what we knew. Right? So I want to write this summation in terms of the summation from 2n to 3n. But that means there's going to be other stuff left over. So let's start doing that. So if I have summation k equals 2n plus 2 of k up to 3n plus 3, if I write it in terms of k equals 2n up to 3n, why am I doing that? Because I have an assumed statement that gives me a formula for this one, so I want to use the formula. So I'm going to have to fix this because it's not equal yet, right? I'm going to have to subtract some things and add some things to make them equal. So to help us figure out what to subtract and add, let's draw a little line here. Okay, so our original summation goes from 2n to 3n. The summation that we want goes from 2n plus 2 up to 3n plus 3. So we're going to have to, so the bottom one is what we know, and this is what we want on the top. So from what we know, we're going to have to subtract these two from the front, right? And then we're going to have to add what? These three on the end. So let's subtract the summation from k equals 2n up to 2n plus 1. And then we have to add the summation from k equals 3n plus 1 up to 3n plus 3 of k. So drawing that picture will really help you figure out and make sure that you have the right kind of overlap. Like, you don't want any overlap. You want to get exactly the numbers that you want and eliminate all the rest. So there's what we have, and we want to use that. Now we know a formula for this one, which was what? That was
5n squared plus 5n over 2.
5n squared plus 5n over 2. This one is just the quantity 2n plus 1, right? Subbing in 2n for k and then 2n plus 1 for k. That's the second one, right? These two underlined ones are the same. Sorry, I know I have some other stuff on here. And then I want to add what? The stuff for the last summation, right? So that's 3n plus 1 plus 3n plus 2 plus 3n plus 3. So I have the left-hand side looking like what I want. Now I just have to get this jumbled stuff to look like what I was trying to prove. Okay, so I want to recombine this. First I'm going to combine all these terms, and then I'll add them all up and try to get a fraction that looks like the way I want. So that's equal to 5n squared plus 5n all over 2. And then that's minus 4n minus 1. And that's 9n on the bottom plus 9n. And 1 and 2 and 3 add to make 6. So then I'm going to combine those terms. That's 5n squared plus 5n over 2 plus 5n plus 5. And then in order to get all of that over 2, I have to multiply these times 2 over 2. So I get 5n squared plus 5n plus 10n plus 10 all over 2. And then that equals 5n squared plus 15n plus 10 all over 2. And I check back up at my proof statement, and I can see on mine and you can see on yours that that is the statement we wanted to prove. So we can put a little check mark because we got the right-hand side just the way we thought. So the purpose of doing that exercise, the main purpose of that, was not the algebra. The main purpose was the picture. The picture where the summations were. Because if we want to add up some numbers and we have to use another addition that was already done, we have to make sure that we subtract things we don't need and add on the things that we do. So I just want to show you the picture one more time. Are you done with this one?
No, 1 minute.
Sorry. You do write really quick.
Coffee.
Can you explain one more time where the I think I understand where the 5n squared plus 5n over 2 came from, but where did the 2n plus 2n plus 1 come from?
That's what I was just about to go back over.
Oh.
Okay.
Okay. So I know I wrote that quickly, but let me go back over this. So a summation is like a for loop, if you remember. Let's get this distracting stuff out of the way. Okay, we have a summation from 2n plus 2 up to 3n plus 3. We want to write that in terms of our summation from 2n up to 3n. But if I look at this diagram, let me make this a little bigger.
Can you move it up to the top of the screen too?
If I move it up to the top, it won't show on TV the right way. So let me, if I can leave it right there, that would be good.
Yeah, not here.
Okay, so right there, if I have all the numbers from 2n up to 3n plus 3 are on my diagram. The summation I want includes the top bracket right here. So from 2n plus 2 up to 3n plus 3. I want that top bracket. I have to take off, so if I'm going to write it in terms of 2n up to 3n, that's marked down here at the bottom with the star. That's the one I already know. If I want to use that one, I'm going to have to take off some things that are in there that I don't need, but I'm going to have to add on the things that aren't. So that's what this second summation is right here. If I put a box around it, the second summation takes off the first two terms. It takes off 2n and it takes off 2n plus 1. So then my real summation I want will start with 2n plus 2. Then I have to add everything up from 3n plus 1 up to 3n plus 3, and that's this last term. So once I wrote this, I know that these two are equal because now I've covered all my bases. I know I start at 2n plus 2 because I took off the things that came before it. And I know I end at 3n plus 3 because I added those on. So then the next few steps were just substitution. This one, we used the assume statement to do a substitution. This one, we expanded the summation. That was the sum of two terms, 2n plus 2n plus 1. And this one, again, we expanded that one, just 3n plus 1 plus 3n plus 2 plus 3n plus 3. We'd have to do different if this wasn't a k on the inside, right? We might have to put f of k, it might be k squared or some other function on the inside. We'd expand the summation. It would have been f of 3n plus 1 plus f of 3n plus 2 plus f of 3n plus 3. Yes?
How can you start at 3n plus 1 and add that in? It seems like you're going to miss the space in between 3n and 3n plus 1.
That's what I said earlier. Like
Okay.
when you're dealing with integers,
So it doesn't
you only
matter?
got a step of 1.
Okay.
Yeah.
We would miss the space if we were talking about real numbers.
Okay.
But we don't miss it because we're talking about integers. 3n, the very next number, if I'm counting, is add 1 to that.
Okay.
Whatever the number is, if you add 1, that's the next consecutive number. So that's why summations are so nice. And that's why we write integrals in terms of summations when you do calculus, because we can actually calculate summations. Because we can forget these things in between the numbers. That's why. Okay, so that picture was the most important thing. So if you have to write a summation that has some more complicated starts and ends, you'll be able to figure out how to modify your summations to use your previous ones that you already know. That's probably the most complex kind of one I'll give you, is one that's like 2n to 3n or something like that. I wouldn't give you something like x squared up to e to the x or something horrible like that. That would be terrible. So you know what to expect from me at least. There's lots of examples in Packet 3.1. There's lots of examples of induction proofs, and they're really well worked out. So if you want to take a look at some of those, they'll help you also with more practice with induction. So let me do next talk about a couple of things from set theory, just to review, and we'll do a set theory proof. Actually, we'll start with a set theory proof. So remember, we have induction and we have set theory, so together we can do some things also. We can prove things for an infinite group of sets using induction. So I'm going to write a problem here. It's probably not going to make much sense, but don't worry because I'll tell you what it means.
To the right.
Sorry, I blew it up. Okay, so we've been doing summations, and summation stood for repeating sums, like plug in k, add the thing. So here what this stands for is do intersection in a for loop. And so instead of doing sums, do a for loop with intersections. So that means these things on the inside ought to be sets, right? So a sub k is a set. So a1 is a set, a2 is a different set, a3 is a different set. And this right here would be take the intersection of these all the way up to an, and then negate that. So that's what the left-hand side says.
Where's the negate come from? The bar?
The bar on the top.
Ah, okay.
Versus the bar down the street.
So this is De Morgan's for a set of n things, right?
Mm-hmm.
De Morgan's for sets.
Is that correct, though, that a sub k is negated? Because the opposite of a sub k, which is De Morgan's, because the bar goes all the way over a sub k on the left-hand side.
Yeah, we're going to do it. Don't worry. I'll explain it. Okay, so remember that intersection was like and, right? So if I did De Morgan's on an intersection, I ought to get the thing that's like or, right? Which is union, right? So this thing on the right-hand side is equal to a sub 1 negated, unioned with a sub 2 negated, union with a sub 3 negated, union dot dot dot, union an negated. So the complement of an. Remember, negation with sets is complement. Or I could use a little c for that, or I can use a bar. It doesn't matter. So ak with a bar is also equal to ak complement, if you remember what that little c is. Okay, so complement was all the things that aren't in the set. So we want to prove that these two things are equal. We're going to need to do it by induction because I have n things, right? So I can't just show by example that this thing works. So I have to do it by induction. So we have a basis. We'll start with n equals 1, which is hopefully going to be a very easy problem. That's what we like about induction. Doing the basis is not too hard, and doing the induction step feels like magic sometimes because you use a formula for something you're really not sure if it's true. Then you prove that it shows the next one, and then modus ponens does all the work for you, which is really nice. So here we have the intersection k equals 1 to 1 of ak, with leaving the bar on top. This is the union from k equals 1 up to 1 of ak with the bar there. But this intersection here is just A1, right? That's a for loop that just does intersections, but there's only one item, so it's just A1, right?
Yep.
So the left-hand side is A1 with a knot, and the right-hand side is A1 with a knot. So that's correct. So anytime we go from 1 to 1 or 5 to 5 or whatever, you just go through the loop one time. Then the next step is to do my assume statement. So I assume that De Morgan's works with these sets. Wow, I don't know why I just wrote that. So I'm just copying over my proof statement. So if you can't read it, copy the top one. And then I need to write my proof statement. So everywhere I see an n, I'm going to put n plus 1. So I do union k equals 1 to n plus 1 of ak, and I'll negate the whole thing, equals intersection k equals 1 up to n plus 1 of ak, and each of the elements inside is negated. I'm sorry, I reversed them. Did I reverse them here? I did.
Yeah.
Sorry about that. I'll write them again. Thank you for asking. Remember, I told you to turn your brain off sometimes doing these things? I think I did a little too much there. So I was just copying over and forgot which one to do. But you could prove that other one I just wrote, right? Guess what? That's on homework 5.
You mean the typo is on 5?
Yes, what I just did.
Okay.
The thing I miswrote, the typo. Yes, that was a problem.
She just gave us the answer. And
Yeah, she could have-
Okay, so now the next thing is to start with what I have on the left. Okay, so that's equal to the intersection k equals 1 up to n of ak. If I intersect the last set, an plus 1, with that, and negate all of it, then that gives me the intersection all the way up from 1 to n plus 1. Notice that that intersect is under the negation.
Okay. So
What did you say about that again? I didn't catch
Intersect.
Well,
that.
this intersect from 1 to n plus 1 is the same as doing the intersection from 1 to n, and then just intersecting the last one on there, a sub n plus 1.
Okay.
And I ignore the knots until I figure all that stuff out, and then I stick them back on there.
So the intersection is counting like as an addition there, basically.
Yeah, the intersect, this intersect works the same thing as summation, but like in my for loop, instead of doing sum,
On the right is we're using as an addition.
this,
Yeah.
well, it's like one more intersection.
Oh, okay.
It's not addition, it's actually just one more of these.
All right.
So this is like intersect, intersect, intersect. Remember what we wrote here.
Oh, okay.
Remember this?
Is that
So it doesn't really matter what it's used as. It's just used as an operator.
It's an operator. Intersect is an operator, just like adding is,
Plus 1. The next
right?
one.
Yeah.
And intersect was like and or times also, remember.
Intersect with one of these.
Okay?
I got 2 of them there.
So
That's from here.
if this was this intersection right here, then I could write it in terms of that one. See what I'm saying?
Yeah.
Let me do that on another piece of paper. So summation, this intersection sign is just like the summation sign. It works the same way. If I have A1 intersect A2 intersect A3 intersect dot 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 AN intersect AN plus 1, that's the same as saying doing the intersection from A1 to AN and then intersecting the last set on there. Right? And I'm just using a shorthand. This is intersect k equals 1 up to n of ak, and that intersects one more thing on there.
like you said, it's just a for loop.
It's just like a for loop,
For
and
n,
this
k
tells you what the
equals
operator is.
K
So
plus
in your
plus
notes,
K less than n.
right, in your notes you have one more operator that's like that. That means times. So in your for loop, it's a pi. If I have k equals 1 up to n of, say, k, that would be 1 times 2 times 3 times up to n. The pi stands for put a times in the for loop instead of a plus. So all of these are just telling you which operator to do a for loop with. So let's go back to the problem we were working on. We have our assume and proof statements. I never ever push the right button for zooming. I always do the wrong one. Okay, so now the next thing we want to do is substitute in for this part, right? But I can't because this is not just by itself, right?
Yep.
This not goes with the rest of the stuff, so I need to do De Morgan's first. But I know De Morgan's for two things, right? I can saw over, because I can pretend this is like an and, I can saw through the bar, change this to a union, right? Intersection. If I do De Morgan's, it changes to a union, and the pieces part fall down. So I have the intersection k equals 1 to n negated, unioned with a sub n plus 1 negated. So the bar falls down and the operator changes. Just like we did De Morgan's with plus and times or and or before, because union and intersection work the same way. So De Morgan's works everywhere. We'll never stop seeing De Morgan's. Now this looks like what my assume statement, right? So now I can do a substitution in there and use my union that I had before. So that was union k equals 1 up to n of a k negated, each of those, union with a n plus 1 negated, which looks pretty good. Looks like I have one more step left to finish my proof. Because this is a union, this goes up to n, that adds on the n plus first one, so I could do the union all the way from k equals 1 up to n plus 1. Because this fits in the formula for the inside, right? This is a sub something with a not on it. So it fits the formula, so I can use the same thing there. That's k equals 1 up to n plus 1. And on the inside, I do a sub k knotted. And that's what I wanted on the right-hand side.
What's the part of having the bar all the way across? We have it squared out, and then you say equals with the bar just over the a and k.
What question are you asking me? How did I go from here to here?
No, well, down one. How did
here
you go?
To here?
Yeah.
Assumed one.
This was my assume statement. So this was by my assumption.
Right.
I did a substitution for this, just the left-hand side. This was the left-hand side of my assume statement.
Okay.
I substituted in the right-hand side of the assume statement.
Oh, okay.
So I used that union. Instead of the intersection negated, I did the union of the negations, the union of the complements. So you thought you had to keep stuff straight before, huh?
So to go from the a n plus 1, you just substitute, you put n plus 1 at the top of the
Right, because this is really the union k equals n plus 1 up to n plus 1
right.
of a sub k with a bar over it, right?
Okay.
A sub k complement.
It's very similar to the summation thing.
It's
basically.
just like summation. It's
Okay.
exactly the same kind of thing.
Okay.
So remember how summation was like a for loop, only we did a sum every time in the for loop?
Okay.
This is just like a for loop, only we do intersection or union every time instead of doing an adding. So they work the same way.
Is it like the next term after n? We have k equals 1 to n, and then the next term is a n plus
Right. N plus 1 is our very next term, so that's why we can put it on top.
1 on top. Good.
Otherwise, if this was a n plus 2, I couldn't just stick it up on top because I would have skipped a n plus 1, right?
Yeah.
So I couldn't put it on the top unless I subtracted it off. I would have had to say k equals 1 up to n plus 2 of a sub k minus a sub n plus 1. So because as I said, these operators work just like for loops, and the variables go up by 1 every single time. It doesn't matter what you do to them. So if you don't want something to show up, you have to subtract it later, because it will come.
Back in the assume, what gave us what let us go from what you have boxed to the next, I guess the n to the or with just the bar over there.
Here to here?
Yeah.
That was my assume statement. I assumed that was true. That was like a given in a proof. That's like a given. So that's a substitution. This is the left-hand side of what I assumed. This is the right-hand side. So every time I see this, I can replace it with that.
Yeah, I understand that.
And that's what I did here.
But when you gave us the problem, was that part of the problem that you gave us as written down?
This
Okay, so that
right
would be-
here, without the assume, that's the problem that I gave you.
Okay. Okay.
Okay, so remember that when we're proving these things, we assume P of n is true. We're proving that P of n plus 1 is true. And our goal is to prove that P of n is true no matter what n is. So we're trying to prove any generic step. If I'm at a generic n, I can go to the very next value. Okay, so take a look at these after you get home, and it might make some more sense. Also, There's a discussion of this in the Rosen textbook. Actually, this very proof is in the Rosen textbook, if you take a look. I'm not sure if it's in the Haggerty textbook. But it's exactly what I wrote here, so you won't find anything different from that. Also, in your notes, there's a example of De Morgan's with ands and ors. So let me zoom in on this. So example 3.8 has De Morgan's. Almost the exact same thing that we just did. This is ands negated on the outside is equal to negating each of the variables and oring them together. So it's really the same thing that we just did.
Okay.
So example 3.8 in your notes is the same thing. Because unions are the same as ors and intersections are the same as ands. Okay, so that was one thing with set theory I wanted to do. One other thing I want to do is called a membership table. So a membership table is like a truth table for set theory. So since all of the things we do in set theory can be written in predicate calculus or propositional calculus, we can also do truth tables with them. So let's try a problem. Let's just say we want to prove that A intersect B, quantity intersect C, is logically equivalent to A intersect the quantity B intersect C. What property is that? Associative. And if you have trouble remembering which is which I always had trouble remembering, I think of associating things. They're already next to each other, but I'm just grouping them with parentheses. So commutative is when you change the order. Associative is when you just move the parentheses around. So if I want to prove this, I can do it with a truth table. But it's not exactly what you might think. In my truth table, I have to say something like X is a member of A. And this is called a membership table. X is a member of B. X is a member of C. These are my inputs. Because what I'm going to do is I'm going to consider all the places where X might come from. It might come from the set A. It might come from B. It might come from C. Now this is a proposition, right? Something's either in a set or not. Now I've converted it into a truth table problem. Now I'll talk about whether X is in this set and X is in that set. And if they're in those sets at the same time, then those sets are going to be equal. So these aren't logically equivalent. They're actually equal because it's not a logic statement, so they're equal. So for shorthand, I'm just going to put X as a member of over this stuff. So this is going to be A intersect B in my next column. And then I'm going to put parentheses around that, intersect C. Then I'll put A intersect B intersect C. And X is in each of these is what I'm going to check. We'll do this just like we do a regular truth table. So intersection is what like what operator? And. It's just like and. And we'll fill this out just like we fill out a normal truth table, binary counting. All right, let's put a line in here so we can keep everything lined up. I'll just go ahead and copy C over again. That's 0, 1, 0, 1, 0, 1, 0, 1. And A over again is all zeros in the top and all ones in the bottom. Now A intersect B is X is in that if X is a member of A and X is a member of B, right? So doing this is just like doing the and of the first two columns. So and preserves zeros, so I get all zeros in the top because X is not in A, so it can't be in the intersection. And then in these next two cases, it's not in B, so it can't be in the intersection. But in the last two cases, it's in both A and in B, so it's in the intersection. Then I do the intersection here. If you look at column number 1, I'll label it here. we're intersecting A intersect B intersect C. We're going to do that intersection. And that's just like ANDing these two columns. So it comes out, everything is 0 except for the last one. And then the very last thing, I just have a couple more things left to do to check if these sets are equal. I have to do B intersect C and then intersect that with A. So B intersect C is just like doing an AND. Seems like this should have had one more 1. That's a 1 right there, sorry. I should have had 2 1s there. C. No, I'm sorry, that's wrong. That's a 0. Okay, B intersect C gives me a 1 here and a 1 in the last row. Then I intersect these two, and I get a 1 in that column. And then I'm going to compare 1 and 2, see if they're equal. And that's true because they're all 0s except for the last case. So I've just done a membership table proof that intersection is associative. So this is the associative rule for intersection for sets. So I could prove any of the rules that I have in propositional calculus. So all of the things we use for the proofs, I could prove them for sets because I have ands and ors in sets also, by using the same kind of truth tables that we did with propositional calculus. But this is called a membership table. But each one is still a proposition because we've turned them into propositions.
So where does X come from?
X is any random element. So if you want to prove something for a whole set, if you prove it's true for a random element, then that means no matter which one you pick out, it's going to be true. So that means it's true for the whole set. So that's kind of another way of doing induction without doing induction. So it could prove it for an infinite size set, right? So this is kind of like doing an arithmetic proof like we did before. We would prove something for things that are in sets, no matter what the item is. This is a way to prove it no matter what the size is. Yes?
Just to clarify, that equal size for the 1 and the 2?
1 and 2. So this one is 1 equal to 2. Or they're logically equivalent, is what we're proving, because then the sets will be equal if those two columns are logically equivalent. Because whenever X is a member of 1, then it's a member of 2. So 1 is this first statement and 2 is this one. So anytime you want to prove two sets are equivalent, you just say, well, whenever this one's in this one, that means it has to be in there, and then vice versa. If it's in this one, it has to be in the other one, so then it's equal. Okay, and you'll use this because on your homework you're going to prove the distributive rule for sets. So almost the exact same thing, only instead of one of these, you'll use A union the quantity B intersects C, and you'll do distributive with that. So truth tables and induction are really important for being able to prove things. And as we said at the beginning of the class, we're always talking about sets of things. We're either talking about finite sets or things that have discrete numbers worth of things, which is integers, basically. So we're talking about integers most of the time in this class, not other kinds of numbers. So when you're worried about gaps between things, remember, integers, you don't have to worry about gaps, unless they're whole number gaps. Okay? So the next thing I wanted to do, we did an induction example. We did some talking about set theory, and I'd like to introduce recursion. But I'll do some simple examples. First, we'll give you a definition of what recursion is and an idea of why we use it. And then next time, we'll do some more complicated things with recursion. So recursion is a really important concept in computer science because sometimes you want to give a rule for making something, but you don't want to specify. So just like in induction, sometimes you want to prove something in a general case, no matter how large your n is. Sometimes you want to be able to say a rule for making something no matter how large something is. So the simplest example of recursion that I can think of is something like 2 to the n. I can define this recursively by saying that that's equal to, like this just helps me figure out how to define it recursively. I just have to multiply 2 times 2 to the n minus 1. If I knew what 2 to the n minus 1 was, I would be done, right? Okay. Now, I told you that recursion's like induction. This would be really nice because I could sort of unroll this. This is also 2 times 2 times 2 to the n minus 2, right? Which is equal to 2 times 2 times 2 times 2 to the n minus 3. Which, if you rewrite this, this is 2 cubed times 2 to the n minus 3. Right? So eventually you would want this one to be 2 to the 0, right? So you have to define what 2 to the 0 is. So in recursion, you have to have a basis. And instead of instead of an inductive step, we'll have a recursive step. So we'll keep working with this example of 2 to the n. So
why did you say 2 to the 0? Did you substitute n with 3? The last paper, if you take about the last paper. You say 2 to the 0.
I said eventually I would want this one to be 2 to the 0, so I didn't have to do any recursive. Right. So I'll talk about that some more because we use recursion a lot with programs, and we're going to need to understand that even better than my explanation just now. So we'll work with it some more. So our function was f of n equals 2 to the n. And we said that our recursive definition was that f of n is equal to 2 times the previous one, which is f of n minus 1, right? Because f of n minus 1 is 2 to the n minus 1. So I can either give you the definition on top, or I can give you this recursive rule, but I have to give you a basis, right? Because if I don't give you a basis, I'll keep decreasing this number forever and ever, and it will keep getting just negative if I go past 0. So I need to give you a basis. So let's say we'll give you f of 0 is equal to 1. So these two definitions are the same. The top one is called closed form. And the second one is called recursive form.
That f of 0 equals 1 is part of the recursive form?
It's part of the recursive definition. Because if I don't have it, it's just like doing induction. Induction, the basis gets you to the bottom of the stairway, and the inductive step tells you how to go from one step to the next. In recursion, this is the same way. The basis gets you to the start of the recursion, and the recursive step tells you how to roll back. So this step says, okay, I can use a previous value, but I have to have a concrete value to go back to. Right, so let's do this again like the way the computer would do it. So in a computer, you could define a procedure, f of n, and you could say return. You could return 2 times f of n minus 1. And this really blows people's minds. Because you didn't actually do any calculating, right? But you have to have a basis in there, otherwise this will run infinitely. Okay, because it will keep trying to decrease this number and figure out a value for it so it could go back and plug it back in. So I'm going to go through a little bit step by step what a computer does when it runs this code. So let me give it a basis because I don't like infinite loops. Okay? The basis says if n equals 0, then return 1. Else, return 2 times f of n minus 1.
So your exit statement is basically what you know from your basis step. It's your exit to get out of that.
Yeah, it will stop the recursion. The basis will stop the recursion, and we'll go through it so you'll understand a little better in the next 15 minutes.
And that's basically what you just proved. Right.
Yes?
That recursion for computers was when you had a procedure that kept calling itself.
That's what it just did. F just called F.
if you just change procedure to function, it's pretty much C++ code.
Right. Procedure,
It's close to it.
function.
Function. Procedures.
That's
avoid
C code.
function.
The same.
Okay. So if I call it a function,
Okay,
it
I see
automatically
it.
returns
Okay.
value. And it would tell, I would say int probably at the beginning.
Okay, I
Do
see
you
it
really
now.
want it?
I just didn't see the
Right.
I didn't see the other function part.
Right. So the function name is f, and so I'm calling f again on the inside, and that's what blows people's minds, because you're like, wait, you didn't tell me how to do that. But the computer knows how to do it, and that's what we're going to do. We're going to do step by step what the computer does, because there's some smart people who figured out how to do recursion. And when I first saw this, I thought it was the neatest thing. So what it does, so when I have this code, f of n, and I say if n equals 1, return, sorry, n equals 0, return 1, else return 2 times f of n minus 1. Let's just do an example where, say, n equals 5. Okay? So what the computer does is it uses a stack. Right? How many people know what a stack is? Good. I'm glad you know what a stack is. I want to tell you again what a stack is so that you think about it the same way I'm thinking of it. A stack is like those stacks of plates at the cafeteria. When you get your plate off the top, it's just like that. You can only take stuff off the top, but you can't see what's underneath. It's kind of scary, you know, there might be some dirty plates in there. But you only get to get the top plate. So if you don't like the top plate, you have to keep taking plates off until you like one.
First in, last out.
Right. The first in is last out. So I'm going to put a little stack over here. This is my stack. And so pushing onto the stack is like putting a plate on top, and popping is like taking one off the stack. So when this gets called, f of 5 gets called. And it goes in here. It says, well, n's not equal to 0. Okay, I need to return 2 times f of n minus 1. Okay, so it says, well, that's 2 times f of 4. And it goes, oops, don't know what that is. Puts that on there. Okay? So it puts that on the stack, and then it goes and runs f of 4. And it knows that it has to return this thing on the stack. So it knows when the stack is empty, it's done running this program. So if you don't put this in there, it will never ever get done. If you don't put this basis, the stack never gets empty because it keeps pushing things on. So what happens is it runs f of 4, and then f of 4 says return 2 times.
I think you just switched your mic off there.
Okay, so the next thing that happens is that I call f of 4 after I push this value because it knows it doesn't know what f of 4 is yet. So it runs f of 4, but that says I need what? 2 times f of 3. So I put 2 f of 3 over there. It says, well, don't know what that is. Better go figure it out. So it runs f of 3, and that says I need 2 times f of 2. So it puts that on there. Says, don't know what that is, f of 2. Says, okay, I need 2 times f of 1. Puts that on the stack because it doesn't know what that is. Now next time it says f of 1, that's 2 times f of 0, so I still have to push that on the stack because I don't know what f of 0 is yet. Now it runs f of 0. And it says return 1, right? Okay, it says return 1. That's good. And then it goes back to the stack and it says, oh, that was 1. Pops this off and gets 2 times 1, which is 2, right? And then this is equal to f of 1. Then it pops, so this is off the stack, and I need to pop 2 times f of 1, right? So, and this was f of 2, so actually this was f of 5. Let me label these. F of 4, f of 3, f of 2, f of 1. The computer doesn't label them because it knows that it put the consecutive ones on there, so it just pops them and plugs them into the next thing. So now f of 2 is equal to 2 times f of 1, which is 2, right? So notice that it doesn't have to remember f of 0 anymore. It's not remembering anything. It's only remembering the thing that it popped off. And it remembers that it needs to use it in the next thing. So f of 2 is 4. Then it pops that off. And then f of 3 it needs to calculate. It's equal to 2 times f of 2, which is now 8. And it's forgetting these things as it pops off, too. Now it knows that it needs f of 4. That's 2 times that number. It's equal to 16. Pops that off. Forgets this. Now f of 5 is equal to 2 times that number, which is 32. And the stack is empty, so it knows it's done, and it returns the value. So it's kind of neat. It pushes stuff on this stack, what it doesn't know yet. It's kind of like what you do at your desk. You know, you pick things up, oh, I don't know that one yet. Don't know that one yet. And you hopefully pop things back off and get a clean desk again. Some of us get clean desks and some of us don't. But the computer, if it has a basis statement, it will get an empty stack. If it doesn't, it will run forever and you're going to have to reboot your machine. So that's how it works. That's how recursion works in programs. So it's very important for us to understand how recursion works, because when you're doing analysis of algorithms, you have to know how many steps this is going to take. Right? If I look at this code, it doesn't tell me how long it's going to run. Anytime you see a recursion, you get suspicious about how long it's going to run. Okay? It might run forever if they forgot the basis. Right? If it goes like this, you know it's going to be some linear time, because it's a linear function of the input. So I knew I had to do 5. Whatever I plugged in, I'm going to have to do that many pops and run the function that many times.
That's an example of what you just did. That's an example of tail recursion, correct?
I believe that is an
Because you do the work on the
example.
way back through rather than on the way out.
Right. I believe that's it, but you'll have to check with your data structures instructor. I don't want to tell you wrong, but this is how it works. Okay. So it's important when we have a recursive algorithm, or when we write a recursive algorithm, we can write a function for how long it takes recursively, and then we want to be able to find the closed form for recursions. So we want to be able to write a formula for them that isn't recursive. So recursive means I have a basis and a step that tells me the function based on the previous value of the function. And in closed form, I have no previous values of the function on the right-hand side. So it gives me a formula. So an example of a recursion is this. If this is my function, f of n, then I can write this recursively, right? Then I write f of 1 is equal to 1, and f of n is equal to n plus f of n minus 1. Okay, and this one we happen to know, since we've proved by induction, we happen to know that this formula is n times n plus 1 over 2. So we can prove, we happen to know, let's prove that these two things are equal using induction. Actually, instead of doing that, let's just do a couple more examples of recursion, and we'll do the recursive proofs next time. So just so that you get more of an idea of what recursion is. So we did do one example, but you want to see some other ones too.
Does this class go over the like which is more like which is better between recursion and doing it non-recursively? I forget what they call that.
No, what we're going to do non-recursively would just be linear in a linear program. So no, we're not going to look at code and figure out which one is better, but what we're going to do is figure out how to find from the recursive definition of like how long some code takes. You should be able to figure out the closed form, and then we're going to teach you how to do big O, which is comparison of growth of functions. So yes, we are going to teach you all of that, but we're not going to start with code and do comparison from that. So what you'll do in your other classes, your very next class, programming class, you'll take two pieces of code, calculate how long it takes each to run, and then you'll compare how long and pick which one you should run. So these things are very useful for when you're designing a program that's going to have lots of inputs. It's very important to be able to figure out how long it's going to run and whether it's the best algorithm to solve your problem or not. And that's really the basis of your algorithms class. So that's actually, I believe, CSC 314. It's not the very first programming class, but the second one. First one, you have to get used to writing code, and the second one, you'll figure out which
It's the
code
data
is the best.
structures class, right?
Yeah, data structures and algorithms. So let's just make up some recursions and figure out some values for them, just for practice. Okay, so here's a recursive definition, and I have to give a basis, or else you don't know when any values are, right? So let's say f of 0 is equal to 1. So let's make a table of n and f of n, just to practice getting some recursive values. So when n is 0, f of n is 1. That's from my basis. When n is 1, I have 3 times this value plus 1. So that's 3 times 1 plus 1, which is 4. The next value is 3 times this value, which is 12, plus 1 is 13. So f of 3 is 3 times f of 2 plus 1, which is 39, plus 1, which is 40. When n equals 4, I want to do 3 times f of 3 and add 1. So that's 120.
161.
161, 3 times this?
20.
120.
Sorry, I was doing 4 times that.
Okay. And then 5 times that one plus 1. I don't want to multiply that.
364.
Okay, so that's 363 plus 1 is 364. So that's an example of a recursion. Let me give you an example. The last example we'll do is just a recursive definition for a set. Okay, so I told you
1 minute, excuse me.
that I could define,
How are you
before I
doing
move
that
this,
so
I'll
quick?
just talk for a second. I told you I could define a set recursively. So I could give you an element that's in a set and a rule for making new elements from something that's in the set, right? So let's say that I have an ordered pair in my set. Let's say that 1, 2 is in my set S. And I'll give you a rule. If Mn is in S, then that implies that m plus 1 n is in S. So this is a recursive definition for a set. I have a basis and I have a recursive step for adding elements to the set. So if I tell you to list 5 elements of the set, first it's very good to just list the first one, right? So S equals, there's one element. What's another one?
2, 2.
2, 2. 3, 2.
4, 2. 5, 2.
So there's 5 elements, so it goes on like that, right? So sort of a closed form way to write this set is x comma 2, where x is in the positive numbers, which I can denote with a big fat P. So we could define recursive sets like a lot more complicated than that one, but that was just an example. So we'll do some more with recursion next time. We'll do some induction proofs of recursions next time, and your homework will be posted tomorrow, homework 5, and you should have all the tools to do that.